Hi everybody, welcome back to my channel on Feynman integration. Today we'll be evaluating two integrals pulled from the channel Maths 505. He solved them using contour integration. I will be using a combination of just plain old U sub for this first one. And then for this one, that will require the Leibniz rule and also some Taylor series. And this integral will be expressed as a sum in the end. This one, I'm not going to spend a lot of time on. All you do is make the following substitution. X is equal to 1 over u, and then you'll find that this is equal to 0. You'll just get back the negative of itself, meaning I is equal to negative I. Therefore, I is equal to 0. So, yeah, that's it. That's it for that one. Now, this one is more difficult. But there's really no re-parameterization you can make on that one directly. Putting a t in there in front of the x is going to be useless because, I mean, you can't take the... You can't get anything useful by plugging in any values for t. Like if you plugged in 0, you'd get negative infinity over x squared plus 1. That doesn't make any sense. And then you could plug in 1 to get you back your original integral, but great. I mean, you can't really make a good re-parameterization. But there is a clue right here in the ln x there on the top. Those ln x's come, you can recover those by taking the derivative with respect to t of x to the t. For instance, if you took two derivatives with respect to t of that, you would get ln squared x to the t. So that motivates us to kind of work an x to the t somewhere into our function of t. So this is what our function of t is gonna be. We're going to create a function of t, and it's going to be equal to the integral from 0. In fact, we're not going to do that yet. Nope, we're not going to do that yet. What we're going to do is we're going to split up j into two separate integrals. The first one is going to go from 0 to 1. And then also from 1 to infinity. I don't remember what rule that's called where you can do that, but you totally can. The integral from a to b of f of x plus the integral from b to c of f of x is equal to the integral from a to c, and we just have 0 to infinity. So we go from 0 to 1, then we go from 1 to infinity and add them together. It's equivalent to going from 0 to infinity. All right, so that's better. Now let's go ahead and make this same substitution into here. So let's see what we get. If we made that substitution just into here, we would get the integral from, let's see, 1 over x is equal to, 1 over 1 is 1, and 1 over infinity is 0. And then we'd have the natural log squared of 1 over x. That would be the natural log of, that would be negative natural log x squared. In other words, you just get back the same thing. That would still be natural log squared x. And in the denominator, you'd have 1 over x squared. Of course, I should be putting u's here, but you guys get the idea. All right, so plus 1, and then of course we'd have negative 1 over x squared dx. All right, we'll use this negative sign right here to switch the bounds. And then we'll distribute that x squared right here as 1 over x squared, I should say. Okay, so we can just replace this with this, but you'll notice that this is the same as this, so it's actually just two of them. So there you go. J is also equal to that. And remember, we started with the integral from 0 to infinity of this, but it turns out that's just equal to 2 times the integral from 0 to 1 of the same thing. So there we go. That's going to be easier to work with, and you'll find out why in a second. It has to do with convergence of Maclaurin series, or Taylor series, I forget. I get those confused. I know the Maclaurin is centered at 0. I'm not sure if our particular function that we're going to be doing an infinite sum for is centered at 0 or not, and I don't really care. Okay, so let's create a function of t equal to the integral from 0 to 1 of, let's see, x to the t over x squared plus 1 dx. Okay. Now from here we can kind of see that if we take 2 times our function f double prime at 0, we will get I. Now go ahead, pause the video and contemplate that for a little bit. If we take 2 derivatives of our function of t, we're going to recover 2 ln x's, in other words, an ln squared x. So we'd have ln squared at x times x to the t. And if we evaluated that at 0, we would get natural log squared over x squared plus 1, which is exactly what we want, except no, we actually want 2 of them. So that's where 2 times f double prime at 0 is equal to I. All right, well, how are we going to take 2 derivatives of this? We could do it directly using the Leibniz rule, but that doesn't help because we would still be left with something very similar to this, in fact, worse. So we need to integrate this directly right now and then start taking derivatives. But, I mean, how can you do that? A clue came, I believe, 2 videos ago, where we know this. We know that on the interval -1 to 1, I believe, with, I'll figure out convergence later. For this sum on that interval, the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x. So I believe the 1 is not included and the -1 is included. So we know that's true. Therefore, on the interval, now we're going to switch. We're going to put this to a positive. All right. Sorry, I'm rambling here. But we can, using this fact, if we just replace x with -x squared, we'll get this. We would get on the interval from -1 not included to 1 included, 1 included, we would have that the sum from n equals 0 to infinity of, let's see, we would have -1 to the n times x to the 2n is equal to 1 over 1 plus x squared. All right. So that is a true statement. So we can pretty much just rewrite our f of t like this. F of t is equal to, we'll still have the integral from 0 to 1. And then let's write this first. This 1 over x squared plus 1 will turn into the sum from n equals 0 to infinity of -1 to the n times x to the 2n, but don't forget we also have this x to the t. That would be out here somewhere, but we can bring it right in since it doesn't depend on n, and then we just get t. And of course, we'd have to have a dx. All right. Now, you'll remember from a couple videos ago, we can use Fubini's theorem on this. We can switch the sum and the integral sign. So let's go ahead and do that. So that would actually be the sum from n equals 0 to infinity times the integral, but you know what, I'm going to go ahead and bring this -1 to the n out here first, then integrate this from 0 to 1 dx. All right, this from 0 to 1, all right, the integral from 0 to 1 of x to the 2n plus t dx is just going to be x to the 2n plus t plus 1 over 2n plus t plus 1 evaluated from 0 to 1. In other words, it's just going to be 1 over 2n plus t plus 1. Right? Yeah. So let's just get that. We'll have -1 to the n over 2n plus t plus 1. All right. There we go. We expressed our function of t as a sum. And since this is just a sum of a bunch of stuff, we can take the derivative of this entire thing directly by just taking the derivative of the inner part with respect to t. So let's go ahead and find our f double prime of t. What would that be? F double prime of t actually, you know what? I just realized something something cool we can figure out right here. We know if we plug in 0 for t, we're going to get pi over 4. So that tells us that the sum from n equals 0 to infinity of -1 to the n over 2n plus 1 is equal to pi over 4. That's kind of neat. I didn't even intend for that to come out of this, but that is true. All right. Neat little side note there. Okay, but let's continue with what we were trying to do. So we need to take two derivatives of this thing. That's going to be very easy. Basically, the derivative of this, we can ignore the -1 to the n as long as we put it back. So let's just take two derivatives of this thing. 2n plus t plus 1 to the -1. Well, our first derivative would just give us a negative sign there. And this would turn to a 2. So that's taking one derivative. Take another derivative. We'll get back a -2, so that will just be 2. And this will change to a -3. So there we go. That's two derivatives of that thing. So now we know that our f double prime of t is equal to the sum from n equals 0 to infinity of, let's see, we can't forget about this part. We still definitely have the -1 to the n, but then that's going to be over, let's see, 2 times this cubed. That's 2n plus t plus 1 all cubed. All right, so now we have our f double prime of t. So we can find I easily by taking this, evaluating it at 0, and multiplying it by 2. So let's go ahead and do that, and that'll be our final answer. So I is equal to, let's see, 4, that comes from this 2 times 2, times the sum from n equals 0 to infinity of -1 to the n over 2n plus 1 cubed. Let me write that a little bit better. Cubed. And that's it. That's the answer. I'm not exactly sure how Maths 505 presented his answer as, but whatever he did present it as, it is equivalent to this thing, because this is correct. So there you go. Those two integrals that Maths 505 solved with contour integration solved a different way. This one very, very, very easy. This one not so easy, and I was unable to get a nice expression for it using Feynman integration, but I was able to get this out of it, which is, that's good enough. You can approximate, if you're an engineer, you can approximate that function very, very closely by just taking the first 5 or so terms of this and adding them together, and you'll get an answer that is extremely close to what you need it to be. And for a lot of engineers, that's good enough. So this might actually be a better answer for an engineer. Anyway, there's my video. Hope you enjoyed that.